Okay, so how is everyone today? Good, I hope. Hope you had a wonderful break. I'm almost recovered from being sick, although I'm not contagious, so don't be worried on that score. I hope all of you were happy and well the whole time. Sneeze. Okay. So, a remark about the schedule. So, of course, we meet Monday, Wednesday, Friday, and according to the numbering scheme that we're using, this week right here was the week immediately before the break, and that was the Friday immediately before the break, and we had quiz 26 on that day. Good. And then 27, 28, 29. Those are the numbers for the days that we weren't here. So that's spring break. So we weren't here for that. And then this is today, 30. So then 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47. So that, number 47, that's the last lecture. That's good. So before we left for the break, the plan was to have a quiz here, but that is not possible, mainly because I was ill. So we're going to move that quiz to right here. So that is to say that not 4 days from now, but 7 plus 4 days from now, we're going to have a quiz 35. Its coverage will be 17 to 25. And we're still going to have a quiz that next Friday. So right there. So quiz 38 will cover, there was nothing on that or any of that. So the first one would be 30 today to 37. And then we'll have a quiz there. So it would cover 39 to 43. All right. And then, the last week we have those 3 lectures there. Pardon me. And then, of course, Mondays, Wednesdays, and Fridays continue to happen, but we're just not going to meet for those. So that one right there is the last day. And then we have that Monday, Wednesday, Friday. So the dates here, so this today is March 25th, and then the next Monday is April 1st, and then the 8th, 15th, the 22nd, the 29th. So the last Monday that we'll have is April the 29th, and then we'll meet Monday, Wednesday, Friday. And the final exam is right here on Saturday. And here's where I like to always remind you that I don't schedule that. The registrar schedules that, and I think it's about as awesome as you think it is, I suspect. So Saturday, May the 11th, is the final exam. So as for the material, of course, 45 to 47, that'll be new stuff you've never seen. in a quiz situation. Then we'll have a few cumulative questions. And the bulk of the pages are going to be redo. That, of course, have the same policy as all the other ones, is that they're optional. You don't need to do them. And if you do them, then it'll be replacement. So grade could go down or up. Okay. Any question about the schedule? All right. Good. So let's get to math then. So on the Wednesday, before the Friday, before the break, we were talking about equations, and that's where we are. Specifically, on that lecture, I was trying to sharply separate two different notions that my experience tells me many students get into this class and the two notions are not separate. So I can write something like this. And then ask, is this an equation? So what's the answer? The answer is yes. It's an equation. So is it an equation? Yes. So for anyone who thinks no, then every time I ask, the answer seems to be that student thinks that I'm asking a different question. So here's a different question. What's the value of this equation? False. So the value of this equation is false. So there's a difference between whether or not something's an equation and whether or not something is an equation whose value is true. So when I ask the question, is this an equation? The answer is yes, because to be an equation, you just need two expressions, a left-hand expression, a right-hand expression, and an equal sign in between them. That's what an equation is. Doesn't say anything about its value. So if when I ask, is this an equation, and you want to say no, then I suspect it's because you hear me asking something else. You hear and think I'm asking, is this an equation whose value is true? Well, in that case, the answer is no. All right. So then I could write a similar one. Write it right here. So 14 equal 14, like that. Okay. So is this an equation? Yes. What's its value? True. Okay, so these two notions need to be sharply separated. Okay. Fine. So among other things, what we did is we talked about equations that have a variable in them in the equation. So we called those equations with one variable or something like that, something obvious like that. And then you can plug in a value for that variable and then ask, is the resulting equation false or true? So maybe it's false, maybe it's true. And if you plug in a value and the resulting equation, the value of the resulting equation is true, then you say that input is a solution. So that's the name for that circumstance. If you plug something into an equation and the result is false, then that's not a solution. So one of the big goals that we have is that I should be able to present you with a variety of different kinds of equations in one variable, and then you perform a sequence of operations so that you can determine all of the solutions. So here they all are. Yes, that's what we want. So to some extent, to some degree, it's like a game, like chess, and like this piece is allowed to move that way, and this piece according to these rules, and things like that. So One of the things that we began talking about on Wednesday, and that we'll retread here again, is that the rules that are allowed. So operations on equations. So here's the main idea. To help you, idea slash physical analogy. There's such a thing as a balance, a physical device. What I mean is, it's like got a little stand, and it comes up like this, and it's got a nice little, fulcrum here, and it's got a little tray like that, and you can put stuff on it. So like you can put a mass right there and another mass right there. And, it's balanced when they're at the same height. And similarly, you can tell if two objects have a different mass, if when you do it, the result is like this. Okay, so to make a physical analogy, what we're going to talk about is all the things that you're allowed to do, and you're not going to change the state of the balance. Meaning that you're allowed to do this, and if it was balanced at the beginning, it'll be balanced at the end. If it was balanced before you did it, it'll be balanced after. And if it was unbalanced before you did it, it'll be unbalanced after. So you're not going to change it. So typical example would be something like this, is that suppose we have an equation, and if you like physical analogies, you can just imagine, suppose that we've got a balance, and on one side there's an A and on the other side there's a B. I'm not saying anything about whether or not the value of this equation is false or true. I'm not saying whether or not the balance is like this or like that. I'm just saying suppose that this is where we are. If we add the same thing to both sides, so that the new left-hand side would be A plus C and the new right-hand side A plus C, B plus C, I mean to say, then that should always work. So if you have a balance that is in balance, if you've got a physical, apparatus like this, and it's currently balanced, if you take two equal masses and you put them on the same side, then it should still be balanced. And if you remove two equal masses from the same side, it should still be balanced. If it's unbalanced, if you add the same thing to both sides, it'll still be unbalanced. So what I mean by that is that concerning this is that if we start with something that is unbalanced, an equation that is false, and then if we add the same thing to both sides, so that the new left-hand side would be 15 and the new right-hand side 16, of course that's false. So it was false to begin with, it was false in the end. Good. Similarly, if we start with an equation that is true, and then we do the same thing to both sides, we add the same thing to both sides, the new left-hand side would be 28, the new right-hand side 28. This is true. So that's good. So now C is just a real number, and because real numbers can be negative, understand that I also mean subtracting things. So you can add the same thing to both sides or subtract the same thing from both sides, and it's always going to be fine. So add and subtract always work. All right, that's good. What did I just do there? That's not right. Of course, this should be 16, right? Y'all gotta catch me when I make a a big error like that. So 14 plus 2, of course, is 16. It's 16, but still true. Both sides. All right. You gotta keep me honest. Okay. So another thing that you could do with a balance, you could say, oh, okay, well, whether or not it's balanced or unbalanced, I could take the masses on each side, and I could duplicate them or triplicate them, right? You could say, I'll just take the mass on the left-hand side and make it 4 times as big, and take the mass on the other side and make it 4 times as big. And it shouldn't change the status of the balance. If it was balanced to begin with, it should be balanced in the end. If it was unbalanced to begin with, it should be unbalanced in the end. All right. So writing that down, that's saying that if we start with an equation, false or true, A equal B, and we multiply both sides by C, so that the new left-hand side is AC and the new right-hand side is BC, then we want to know under what circumstances is this going to work. And you might initially think that it's going to work under all circumstances, like add and subtract to, but that's not the case. To see some instances where it does work, if you take an equation that is false, and you multiply both sides by 2, say, then the new left-hand side will be, for this one, will be 16, the new right-hand side, what am I talking about? My goodness, I'm having a lot of problems here. 26, 28. All right. So the result is false. So that's good. So we started with false and ended with false. So that's good. Similarly, if we take an equation that is true, multiply both sides by the same thing, then the new left-hand side is 28, the new right-hand side is 28. True. So far so good. Meaning that this thing that we're doing, if it was false at the beginning, it's false at the end. If it was true at the beginning, it's true at the end. So that's good. But however, there is something that we can do. There's some C for which this isn't going to work. What could break this? 0 can, because if we start with an equation that is false, so that's false, and then if we multiply both sides by 0, then the new left-hand side is 0, and the new right-hand side is 0, and so that's true. So notice that we started with something that is false and ended with something that is true. That is a very notable circumstance. That means that in some sense, if you think of it like a chess game, you performed an illegal move. You can't do that. Now, if you like the physical analogy, what this is saying is that if you have a balance, and it's either in balance or out of balance, then you can take the masses and you can multiply the masses by 2. That's fine. It's not going to change the result. You can multiply it by 22. That's fine. It's not going to change the result. But here's where the physical analogy kind of gets a little hurts a little bit. Is that okay? What if we take the masses and we multiply them by half? Well, it's still going to be okay. But if we multiply a mass by 0, then that would mean like essentially removing the mass. So what if we took a balance that would, apparatus that was out of balance, like this one, and we multiplied the left mass and the right mass both by 0? Physically, that means let's take the left mass and the right mass away. Let's take them away. Well, it's going to be balanced after that. That's what this is saying. All right. So what this is saying is that concerning equations, you can multiply both sides by a number as long as what? As long as the number is not 0. So this is you can think of this as like this is another move that's allowed. This is another legal move when C is not 0. And you need to understand that, for each one of these moves, going in this direction, that's adding c. So we're saying that adding c is fine. And going in that direction, that's subtracting c. And we're saying that subtracting c is fine. Here, what we're saying is that for this one, multiply by c is fine. And going that way, divide by c is fine, as long as c isn't 0. So this thing right here, this is yet another algebraic manifestation of why it's not permitted to divide by 0. Because going this way, that's division by 0. Multiplication by 0. But when you go that way, that's dividing by 0. If it was allowed for you to divide by 0, then you could conclude that 13 is in fact equivalent to 14. Okay, so not possible. It's not a legal move. All right. Fine. So another move operation on equations that we're going to want to do is that we're going to eventually get to some equations that have radicals in them, like square roots and things like that. So if we want to undo a square root, then we're going to have to square. That's sort of the undo for that. So, we want to square both sides. So square the left hand side, square the right hand side, so that this would be a squared is b squared, like that. And we want to know under what circumstances is this okay? All circumstances, just some? All right. So if we start with a false equation, 13 is 14, and then we square both sides, the new left-hand side would be 169, and the new right-hand side would be 196, and that's false. So that's good. That's good because, it was false at the beginning and at the end, so we didn't violate anything. Similarly, we could start with an equation that is true. And square both sides. And get 196 equal 196, which of course is true. So that's good. So, the fact that it went false to false is good, and the fact that it went true to true is good. If ever it switches, that's a problem. So there's a way that we can break it. There's a way we can make it switch. Specifically, we can make it switch from false to true. How can we do it? In this case, 0 is not going to be a problem. In this case, 0 is not going to be a problem. So here's the idea. Imagine that we've got a squaring machine, and it's like a huge building. It's like enormous, and you put inputs in on one side, and then the outputs come out on the other side. So you're not big enough to be able to see both sides. So you're standing over here. So inputs on that side, and then outputs come out over here. So what I'm saying is that if you put a 3 in on this side, then a 9 is going to come out on the other side. And if you put a negative 10 in over here, then a 100 is going to come out over here. You're going to square it. So now, suppose that this is you're right here on the output side. And suppose that you witnessed a 16 come out. Then do you know for sure what was put in? No, you can't be certain, because there's in fact more than one possibility. If you witnessed a 16 come out, what could have been put in?
4 or negative 4?
Yeah, either one of them, 4 or negative 4. So you can't be sure. All right, so that's a pretty big hint. What equation can we use? To go from false to true. All right, I like it. So negative 14 equal 14. So, there's an equation. Its value is false. This value is false. And now let's square both sides. Okay, so the right-hand side is easy enough. It's 196. The left-hand side is just slightly more difficult. What's its value? Also 196. So, you know, this one is true. So we started with false, and we got true. And that, you know, that's a notable thing. That's like, oh, I made an illegal move, in some sense. So under what circumstance is it permitted for you to square both sides? When's it going to be okay?
When they're not opposite integers.
So I'll rephrase it like this: when they have the same sign. So both sides need to be positive, or both sides need to be negative. Either situation is fine, but you can't have 1 and 1, because if you ever have 1 and 1, like so, then it's possible to go from false to true. All right. So we're going to be solving lots of equations from here on out, and we're going to have, you know, there's going to be more than these 3 moves. We're going to come up with more than this, but for now you can just think of it like these are the only 3 things that we're allowed to do. And one of them is always going to be fine. Like you can just use it without a care. So this one's always safe. This one, we're going to need to use it. We're going to need to do multiplies and divides. But you have to be a little bit careful when you do it. Because if you're not sure that this thing that you're multiplying or dividing by is non-zero, then you might have broken something. And similarly, we're going to need a square. So what will happen is that we'll perform these operations, and anytime we need to do one of these potentially unsafe ones, we'll make a little mark and says, oh, look, you know, I had to do that, and that might not have been completely okay. So now I have to do a procedure that goes back and checks whether or not doing that was okay. All right. So to that end, there's something called a linear equation in one variable. So I can say let A and B be in the reals with A and B are constant, so they're just some constant values, and A in particular is not 0. Let W in the reals be a variable, meaning that you know, there's going to be 3 letters, but only one of them is going to be construed as being a variable. The other 2 are positive. The other 2 are constant, I mean to say. So here we have it. So A multiply W plus B equals 0. So that's a linear equation in one variable. For reasons that aren't entirely clear why we're using the word linear. But anything that can be written like that is called a linear equation in one variable. So these are like the simplest possible things that exist. So so there's not a lot to say about them. But if we wanted to solve for W, which is to say, take this equation and you know, notice that W is not by itself. It's got the, you know, it's got multiplies and adds and A's and B's all around it. We want to get the W all by itself. That's what is meant by solve for W. How do we do it? Well, in fact, we've done this multiple times, even this semester. So, I know that before you even got to this class, you could tell me, well, the first thing I need to do is I need to subtract b. Okay, no dispute. That is the first thing you need to do. But now I have a question. Why is that the first thing you need to do? Why? Okay, well, so I'll rephrase my question. I can see that W is not by itself. I can see that it's got some multiplies and some adds and A's and B's. I can see that all those are there. And you're telling me that the B should go first? Well, A seems to me to be before B in the alphabet, right? What is it? Yeah. So now, concerning the order of operations, we talked about that a bunch, and we had a question where it was give you this expression and then analyze it and label each operation with its PIMDOS label, right? And then the question always was which operation occurs first. So considering that, as this expression is written, there's two operations, a multiply and an add. And in the order of operations, the multiply comes first. But now to solve, in fact, the way that you do it is you still consider the order of operations, but now you ask which one is last. Instead of actually asking which one is first, you ask which operation is last. So there's two operations, a multiply and an add. Which one is last? The add. So the add is what needs to be undone first. So it's just like an onion, right? If you wanted to disassemble an onion, well, you do it from the outside, right? You peel it. Same thing here. If we want to get that W by itself, we've got to undo the order of operations in reverse order. So the reason why we do this first is because I like the phrase that he used, reverse PIMDOS. But be careful, and remember that the order of operations isn't exactly PIMDOS, right? It's got the M's and the D's are tied and what have you. All right, so we do that, and so then we have AW is negative B. All right, good. And then okay, we want to solve for W, so I'll divide both sides by A. So that we get W is negative B over A. Now, to do that, we divided by A. And we just got finished on the previous page saying that it's not always all right, apparently, to divide and multiply by a number. What gives us permission to do that here? Right, right there at the top, at the outset, we said that we're talking about an equation where A isn't 0. That's our permission to proceed. That's what makes it okay. Okay, and so there's like nothing more to say about linear equations in one variable. I mean, this is it. The only interesting thing I would say, notable thing, is that when you want to do this, the operations that you perform, the order that you perform them in is reverse PIMDOS. All right, fine. So here's an entertaining way to see how bad this can break. So like in my family, I'm like the only mathematician, and that's usually the case. Not always the case, but very often, if you're a mathematician, you're the only one. So as a result, anytime any of my acquaintances and family members and what have you see one of those images on Facebook or whatever where there's any kind of math or whatever on it, it just immediately straight to me. So that's an aspect of my life. Fine. So one of them I have received so many times that I actually have it memorized. So it's the following sequence of operations. So I want you to consider what's being written here. So in the first place, we'll say that let A and B be in the reals. And suppose we start with this. Suppose that we say A is B. A equal B like that. So now I'm going to do some operations. The first thing I'm going to do is I'm going to multiply both sides by A. All right. So I do that. The new left-hand side is A squared. The new right-hand side is AB. All right. So now I'm going to subtract B squared from both sides. Fine. So the new left-hand side is A squared minus B squared, and the new right-hand side is AB minus B squared. Okay. Now, early in this semester, we considered expressions like that, and like this, for that matter. So, I'll deal with this one. This one's a little bit simpler. Do you observe that we can factor this because there's the greatest common factor? What can we factor out? B. Okay, so I'll do that. I'll leave the left-hand side alone. So I'm not playing with that. And then concerning the right-hand side, we can factor out B. And if we factor B out, then what goes right there? A minus B. All right. Great. So again, if you're dealing with a balance, then the analogy to equations is that if you're doing something only on one side of the equation, it's always legal, because if you take a balance and it's either in balance or not, if you take the masses that are on one side and just move them around a little bit, that doesn't change whether or not it was balanced. So this is just messing around with one side. So that's fine. That's fine. Now, concerning this, A squared minus B squared, we've got a name for that. We refer to that as the difference of squares, because that's notable enough. And, more than that, we know how the difference of squares factors. So how does this factor?
A plus B, A minus B.
Yeah. So it factors as the product of conjugates. So A plus B multiplied by A minus B. So, from humble beginnings, we've, gotten to something, we've gotten to this place. We factored both sides. And now, hey, look, there's a factor of A minus B on both sides. So this side has an A minus B factor, and that side has an A minus B factor. That's like if both sides had a 5, right? Like this one is something times 5, that side is something times 5, and this other side is also something times 5. So, let's cancel that. So I'm going to divide the left-hand side by A minus B, and also divide the right-hand side by A minus B, so that we can cancel that. Now, if we cancel that, then what will the new left-hand side be? A plus B. And the new right-hand side will just be B. And now, for reasons that aren't entirely clear, I'm going to remember that. You remember at the beginning when we said that A is the same as B? So that means that it's all right for me to replace that A with a B. So I'm going to do that and say that this is B plus B is B. And so then 2B is B. And now look, there's another common factor on both sides. So I'm going to divide by B. So when we divide the left-hand side by B, what's the new left-hand side? B2, right? And what's the new right-hand side? 1. That's a little disturbing. So clearly something is not entirely all right with what's written on the page. Something's not okay. So the point of me writing this down is to show you that, I mean, I did a sequence of operations here. You know, and I didn't do them in any particular rush. And it can be kind of hard to spot exactly where it went wrong. So where did it break? Where did we break it?
B squared.
With this one? Okay, so that one's actually all right. Because if you look at the, you know, if you think of it like a game, you got the 3 moves you're allowed to make. You know, we've got the add and subtract move. That one's always okay. It's always safe. And so that one is actually fine. So maybe. So what do you mean? Taking a shot. Okay. Well, so like the step from here to here. So ignoring all that stuff, just remembering that that the difference of squares factors into the product of conjugates. That's fine, because if you like the balance analogy, that's just saying that on one side of the balance we just fiddled with the masses. We just moved them around a little bit. So that didn't change. Doesn't change anything. So that factorization is fine, and that factorization is fine. But in fact, there is something that's not okay about the a minus b and what we did with it. So, you know, add and subtract is always safe. Multiply and divide, not always safe. So what is not permitted concerning multiply and divide?
When you divide it by a minus b,
You're saying, well, you're saying that's not all right?
isn't it because a is equal to b? Doesn't that equal 0?
You remember at the beginning when we said that a was b? And so that means that a minus b is 0. So right there, that's divide by 0. That's where we broke it. Can you see that it can be a little bit subtle and hidden? So the problem is right there. Is that a equal b means a minus b is 0. So that's a divide by 0. Now, to make it a little bit less obscure, I could write an equation like this. I could say, well, 13 multiplied by 0 is 14 multiplied by 0. So is that an equation? Yes. What's its value? True, because the left-hand side is 0 and the right-hand side is 0. So this is an equation that is true. And now I can look at it and say, hey, I noticed that there's a 0 on both sides. I don't like having the same factor on both sides, so I'm going to divide both sides by that factor. And ignoring, for the moment, the impossibility of doing that, if you were to just say that, okay, well, I'll just write a new equation where that's not there, then that would mean that you would write the equation 13 equal 14, which, of course, is false. So, you know, this is not okay. All right, so good. Any questions about this example? So we'll have something where I give you something, you know, it's like a seek and find. You got to find, you know, where did we break it? Because we started with something that is true and then ended with something that is false. Okay. So another thing that we're going to want to do is deal with equations that have 2 variables. So it's exactly what you think. It's an equation, and now instead of there just being one symbol, now there's going to be 2, like x and y or P and Q or whatever. There's going to be two of them. And now we plug in points. Not individual numbers. So, to give you an example, if we have the equation, say 3y minus 5x is equal to 9. So there's an equation with two variables. Then we could say, well, you know, you could plug in xy equal to 6, say. So when you plug stuff in, you know, you got to say, well, what are you gonna put in for x, and what are you gonna put in for y? The result when you do that can be false or true. So I'll do that real quick. So 3y, replace all y's with 6, minus 5x, replace all x with 2. So this would be 18 subtract 10 equal 9. So 8 equal 9. All right, so that's false. Plain. But just as well, I could say, well, plug in xy equal to 0, 3. And then, all right, well, in that case, 3 multiply 3 subtract 5 multiply 0 equal 9. And of course, now it reads 9 equal 9, which is true. All right, so sometimes you plug in points, the result will be false, and sometimes you plug in points, the result will be true. All right, so to that end, the way that this is usually discussed is like the following. So I could say, let y be something like 2x minus 3. And we could go down the list, and I could say, well, plug in this xy, plug in that xy. You know, we could just plug in a bunch of them, and sometimes it'd be false, and sometimes it'd be true. So to sort of shortcut the matter, I could say, well, I'm going to make a table, and it's going to be partially filled out, and I want you to complete the table so that every point that's in the table, when you plug it into the equation, it would be true. I'm not interested in any of the false ones, just the true ones. So I can, you know, plug in when x is negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5. So what I mean by that is that, you know, I gave you a nice equation, relatively simple because one of the variables is solved for. So what I want you to do is plug in this value of x and then tell me the resulting value of y. Okay, so that would be, in this case, so negative 9 and then negative 7, negative 5, negative 3, negative 1, 1, 3, 5, 7. So what I mean by that is that if you select any one of these, if you plug in xy is 2, 1 into that equation, the result will be true. That's what's meant by the table. So now, those are points in the same kind of way that we've been drawing points on the axis and asking, well, where is that point? So if we take an axis and plot all those points, then the result looks like this. So 2, 1. So 2, 1 right there. That's where that one is. And then we could, you know, just continue this, right? 3, 3 right there, and there's one there, there, and there. So those are the only ones in the table that will fit. Now, we could you know, instead of plotting just these 6 points, we could plot 6 million points. But generally speaking, once you've plotted enough of these, for simple cases like this, you can just connect the dots. So these are connected like this. And here's what I want to make sure you understand. The distinction here is that the set of all points for which the equation is true is called the graph. Of the equation. So what we're going to do, a big task that we're going to do for the rest of the semester, is we're going to take equations, we're going to want to solve them and things like that, but we're also going to want to make pictures of graphs. So a picture of a graph is called a plot. And the connection is this, is that these are all the points on the plane. For example, here's one of the points. Now, I happen to be pointing at, it looks to me like -½ 5. So if we plug -½ 5 into that equation, will the result be false or true? It will be false. What if we plug that point into the equation? Will the result be false or true? True. What if we plug in that point? True. What if we plug in that point? False. What is this picture? It's the picture that you get when you say, I'm going to color every point so that the equation is true. These points over here that are not are not colored, like this one, this is where the equation is false. It is true exactly and only right there. So a big task for us is going to be able to take an equation, identify it, and say, oh, I know what its picture is going to look like. And I can interpret the result of the equation, false and true, from the picture. All right, so that's it. I hope you have a wonderful Monday.